or you recall if you already know some of this, the definition of for the universal centralizers. This is associated to any complex semi-simple Lie group G. Okay. So or more general reductive ones. Okay. And then I will present some results on its geometry. So on its symplectic geometry. And with the goal of proving homological mirror symmetry results. That's the goal for today. Okay. So maybe this can be lifted. I should lift. So first definitions of the universal centralizers. Also, so maybe first some motivation. So making example. Homological mirror symmetry. So this motivating example is from like the abelian version where we have the well-known theorem that that if you consider a complex torus.
Want me to move that?
I can get. Is there a place?
Yeah.
Yeah.
I can. Oh, that's what. Oh no, that's okay.
I see. That's good. I thought they were make a knot or something.
Well, not me.
Oh, then we cannot reach it to put it down. Okay. So yeah. So T is just complex torus. Then in this case, the symplectic variety is we consider as the coordinate bundle of this torus, and that is actually a abelian version for this centralizer universal centralizer. And then there's a homological mirror symmetry result saying that some version of the so-called Fukaya category of this coordinate bundle of this torus is called the equivalent to the derived category of coherent sheaves on the dual torus. That's some classical or maybe well-known result. So roughly speaking, the equivalence is established as follows. So this relative category that we will like suppress the definition for now. It's some symplectic invariant, but it's like of a topological flavor, and so then one can identify this category with the DJ category of local systems on T. Maybe only consider like the compact objects, so all local systems, but the compact objects. Then this is equivalent to modules over Taiwan T. So again, PG and the compact object. Then this is the function ring for T check. So then this gives the identification. Okay. So yes. Then this is the motivating example of homological mirror symmetry. Then our goal is to generalize this to the non-abelian version where this T star T is replaced by this so-called universal centralizer for semi-simple liquid or reductive liquid. Okay. Great. So part one is some definition of this centralizer. So so there are several equivalent definitions. But here we'll just highlight two of them. So the first one is indeed explain this centralizer property. So this so first you consider this regular locus of the bundle of G. So then you identify with this using that translation, and then you take a subvariety of it. So consider pairs like that. Co-adjoint cosine, then centralizing a pair inside it. So this is regular. Then have this subvariety, and then you can and then there's a natural adjoint action on it, right? So it's adjoint on both G and cosine, observing this identity. So then and then you do a GIT quotient. So by this adjoint action. This is a smooth. So actually, this is the definition of G. So it's a smooth affine variety, and actually it's like homomorphic symmetry. Definition.
Sorry, I have a small question.
Oh yes.
When you do the GIT quotient, what specific character are you using? I mean, are you
Just the naive one, the G invariant function.
trivial character? Oh, I see. So it's not the GIT; it's just the categorical quotient.
Oh yeah, categorical quotient.
Yes, you said GIT, I think.
Is it the same? Yeah, I think it's the same in this case.
Oh, I don't know much, right? The GIT, I think you take the semi-stable points, etc., etc. I mean, that's not what you're doing. You're just taking you're taking the spectrum of invariant functions, right?
Yeah, yes.
Yeah, okay. So maybe that's the same for the trivial character. Okay, anyway. All right.
Okay. Great. So then yeah, from this description, one gets a map to the adjoint quotient. So to the adjoint quotient by like just sending C to quotient of the C, and then it turns out that this is this is a abelian group scheme. So each fiber is just the centralizer of G. It's a group abelian group scheme. And then and then just to show a picture. So so for SL2, then the base is just A1. So then the determinant of the traceless matrices, and then we have the generic point. So this corresponds to the conjugacy class. This one, a generic one. And then, so then here, the centralizer is just a maximum torus. It's a C star here. And then for the central one, so this is represented by the regular nilpotent element. So this is this class. Then, and if you calculate the centralizer, then it's actually two A1s, strong A1s. So then one is one star, the others. Then then this is the smooth vibration. Okay. And yeah, so then this is a linear group scheme, and actually this is an integral system, complete integral system. And another feature about this is that we have two sections of this vibration, so each corresponding to a center element. And this is given by it is called the constant section, given by the essentially given by constant size. So it's like
Sorry, I'm afraid the red is not very visible on the video.
oh, I see. So maybe this is better.
A little, yeah.
Okay, I'll use this. So
Sorry, I have another question.
please.
I'm afraid it's probably embarrassing. I missed something really very simple, but so the universal centralizer is maps over the regular points in G star, right?
Maps. Sorry.
Yes. When you take the projection to C.
Yes. Yeah.
Yes.
So the only here are regular, but it covers all the the code. I mean this code image of cojoint quotient. I mean, each one is represented by each class is represented by unique conjugacy. I mean, regular conjugacy, regular orbit, regular cojoint orbit.
Okay. All right. Sorry. Okay. Thank you.
So yeah. So actually, there's this constant theorem that. That's just consider the constant slice. So this is from principal SL2 triples, and then you can consider. Then you can consider principal SL2 triple. Then you have the constant slice. This actually. They are all regular, and then this project to C, and then actually the composition is at the moment. Great. So any other questions? So then if you use this constant slice, then there's actually a simpler description of this. Okay, so it's just like centralizer of the constant. Much simpler, so there's no categorical quotient involved. Okay. Simpler. And then okay, great. And this is definition 1. And then for definition 2, so this is given by, so then we can, so for definition 2 is realizing JG as a Hamiltonian reduction of T star G, not like a T star regular. Oh. We met before?
Yeah.
Oh. From UIUC, right?
Yeah.
Oh, yeah. See somebody here. So definition 2 is that this GG is Hamiltonian reduction of. So yeah, so again, this definition is based on Constant's theorem. So like based on the property of this constant slice. Okay. So then maybe let me just say what it is. So so we fix this principal SL2 triple. So then again, this. So using this, we can determine this which is a centralizer of H, and then we have this row. So yeah, it's like the simple roots are the like for the decomposition for E. Then and then we have G. So then, and then yes, then and then corresponding group. Well, we call them radical. Then yeah, well, once we have this, so once we have this, we can consider the Hamiltonian action by the important radical, the left and the right action on G and the Hamiltonian ones, and then standard that the moment map is given by so if you do the use maybe shading form and then opposite, then this is like mod E. The left and the right moment map, and then here we think so here F is in this minus. And then this is actually a regular the algebraic character of n. So then we can do Hamiltonian reduction. So this yeah so n is in this case now we can form the Hamiltonian reduction. So it turns out that it's mu inverse FF smooth, and then the n cross n x affiliate on it. So then the quotient is smooth symplectic variety. We have a nice quotient. Right. So any questions? So then actually, if you use the top descript this you use this one, okay, and then you use some property about this. Yeah, about this. So essentially use property that is L plus B is like n times the constant size. And use that, then show that these two are identified. So these two definitions are the same. That's essentially. Great. So very good. So now let me say some other one more thing about this setup. So yeah, there's a natural C star action on so which will be used for setting up the Foucault categories. So we use this. So this roughly is just given by, so you have this this H. So this is like a 2-row check in the co-root lattice, and then this gives a one parameter subgroup, and then you can consider action here. So here we use this Hamiltonian reduction description. So yeah, so like C is in like F plus B plus B, and then here we just do so. Do the adjoint action on G, and then essentially the adjoint action on C, but here because the adjoint action will scale up by like weight -2, so you need to multiply by squared compensation of that. And then this gives the action. And then the property of this action is that it scales the natural symmetric form, so descended from GPRT by weight 2. Essentially because of this square, it's like dilate the fibers by weight 2. Right, so that's the C star action, and then later on, what we will use. This one is that if you take the take only the R plus action, so only you take R plus action here, and then you take maybe the square root, so that it has a weight 1. Okay, then you take the square root, that's weight 1. Then it's actually a Liouville vector field, so-called Liouville vector field. So essentially, I mean, it's just defined by that it scales omega by weight 1. So it's the derivative of this vector field generating this thing is omega. That's the definition of Liouville vector field. That's what we later. So any questions? Great. Let's do this.
Sorry, what was that equation?
The
LZ of omega.
It's omega. Yeah, Lie derivative of omega is omega. So that means if you exponentiate, then scale by weight 1. So so maybe let me just write down the main theorem. So first this we show that the first statement says that we can define a proper version of category on this symplectic variety, because it's not always the case that we can have a well-defined category. So yeah, and then this is through some real partial compactifications of partial by some with real boundary, which should be a so-called Liouville vector. So then by results of Harden-Schende. Also, so once you know your variety is a Liouville sector, then you can define a so-called partially rectified category on it. Yeah, later on we will refer to this group by GPS. Appears later. So and once we have this category, we can ask what is this category. So it presents some feature of homological mirror symmetry. So the statement that it's equivalent to coherent sheaf. So let's me first to do the adjoint case, and then this is coherent sheaf on the dual maximal torus in the dual group of GX, so the simply connected one, denoted by simply connected. Then this is quotient by GIT. And then if you do general G, then you have this covering on this G add, and then here on this covering connected. Then in this case, so this is equivalent to coherent sheaf. So here you have this you have this pi 1 of check x on this thing. Actually, it's yeah, the x on this on the maximal torus. Okay. So then it commutes with the Y group, and then here we form the equivariant category of equivariant coherent sheaves on this which is actually this is just the affine space. One thing this is natural because is that if you do the naive P check, this thing is singular, but in general this category will give you a smooth. In general. This is get right. So maybe just a remark on some related results, which is in the more algebraic version of this, people are more familiar with, like modules.
Sorry, I have a question.
Yes, yes.
I assume you're going to explain what a Liouville sector is and what the partial compactification is.
Yeah, I will explain.
Yeah, okay, yeah.
Okay.
Yeah.
Thanks for the question. Okay, great. So, so this remark about just algebraic conversion. So they show like the module Whittaker modules. This is equivalent to like some quasi-coherent sheaf, quotient like T star given by Wi prime. Rough. I will not explain this. Okay, so it's like I mean, I will just say. Roughly something like this. So then analytically it recovers like T check over quotient by tau. So some relation, some non-rigorous relation. And this idea is like corresponding to Foucault category, like on the Hamiltonian reduction. However, there's no direct link between algebraic version of, for example, this category with coherent sheaf. Great. So this is remark, and right. So now let me go to the symplectic side. As sorry, I forgot your name. Valerio asked about this Liouville sectors. So background on this Liouville manifolds or sectors. And then maybe a few words about how you define the category. The first, the starting point is this Liouville manifold. So it's a symplectic manifold. I mean, it's like the equivalent way to say it, like you can say it's a symplectic manifold with a Liouville vector field, or it's, I mean, the first data is equivalent to say that you are given a one form, so that this is omega is the alpha, and then this z is related by z is coming from uniquely determined by alpha. Equivalent definition. So this is one data. So you have a Liouville. So maybe you call this as Liouville form. And the z is the Liouville vector field. And then this is so then this is not enough. So we also need that the Liouville vector field is so here you should decompose your symplectic manifold as some maybe compact part with boundary, and then union with some cylinder over this boundary. So union with a cylinder over the boundary of the thing. And then the property is that so for this boundary, you should see that the z going outward here, and then the completion of the z gives the cylinder. So this is Liouville dimension.
So for example, could I take the cotangent bundle of any manifold?
Yeah, exactly.
and
Yeah.
Take the scaling action on the fibers. and
Yeah, exactly. Yeah. Very good. Yeah, Peter said so. Yeah, that's exactly the motivating example. So it's like here you can take any closed manifold, and then the alpha will be like PDQ, and then the Z will be the scaling on the fibers. Great. So then another example is one that you have this R2N, and then you can have this scaling this dilating action, and then here the alpha is 1/2 PDQ minus QDP. Another example. Great. What should we put in a lot of lift? So okay, so maybe for later purpose, let me just highlight a nice class of Liouville manifolds, which can be understood from handle attachments. It's nicer, so-called Weinstein manifold. This is following work of Beck and Ashworth. So they have a book on this topic, Weinstein manifold. And,
longer chart, it's some of the box.
oh yeah, yeah. I just want to use this nice chalk, the Japanese chalk, but
There's also some in the Crayola box right there.
But it's not the nice stuff.
That's true.
that's fine.
Okay.
So yeah, this is so then so then maybe the more intuitive way to characterize this is that one can understand. So they are these are built from handle attachments. So, like one that in Morse theory. So essentially, it's I will not go to the detail, but every such thing can be built from. First, you have maybe zero handle of it. So zero handle in this case will be just R2N. The example is so here. This is the zero handle, and then you have handle, and then you have this so-called contact boundary. Then the Liouville manifold nice thing is that if you have such a Z, then this for the infinity boundary, this is a contact manifold. That's the nice. The contact manifold has this canonically given contact form. Okay. And then to build further, then what you do is that you choose some like so-called Lagrangian submanifold in it. So which is like, so if you take the cone to build that Lagrangian. So Lagrangian means that the maximal integrable sub manifold to the, I mean, let's say it's like lambda alpha restricted to Lagrangian should be 0, and the lambda is maximal dimension. So it's this is 2n minus 1. The lambda dimension is minus 1. So that's maybe it's a projective version of Lagrangian. So that's the relation between a symplectic and the contact. Right? So yeah, so then the next thing to do is to choose some Lagrangian like a sphere, and then take a neighborhood, and then you attach a handle to it, and then yeah, but yeah, what I said is critical. So in general, you can do like not necessarily Lagrangian, like maybe some s where alpha is 0, then you can do handle, but then it's like index lower handle. So it's then yeah, you can attach different handles with different index. The index is the dimension of the standing manifold here. And if your handle has a lower index, then here it will have like lower dimension. The maximal dimension is the Lagrangian case. That's the maximal dimension index handle you can attach is this this one. Okay. And then in that case, you get here, you get a Lagrangian here because it's dimension n. Right? And then in this case, it's called a critical handle. Here, next is maximum index is n. So the index is the dimension of this thing. Okay. Attaching locus here has dimension minus 1. And then max index is n, and then in this case it's called a critical handle. Then it's understood that the symplectic invariant, I mean, so I'll say these give interesting symplectic invariants. So just say the general philosophy is that if you have handles that are all below this index, so so-called subcritical, then the symplectic invariant is trivial. So, for example, your Foucault category is always trivial. But, yeah. So if you have a wall, then it's always have trivial Foucault category because it's index 0. So it must be a middle index to have a non-trivial Foucault category. It's just a handle attachment. So
you're saying that Weinstein manifolds can be built with a single zero handle?
Oh no! Attach a lot of handles. So inductively attaching handles.
Sorry, but you have zero handles
and then maybe index 1 handle attaching on like some yeah. Yeah, up to n handles. So you attach 1 handle, and maybe here my picture is too low dimension, and then I got new contact boundary, and then attach higher and index higher, just like Morse theory.
So it sounds like it's very analogous to Morse theory.
Yeah, exactly. Yeah, analogous to Morse theory. Yeah. So it's like yes. Then here you get the ascending manifold. The core of the handle is the part of the ascending manifold. Then you attach higher and higher index. But the thing here is like, yeah, actually it's more like Steiner manifold. then the handle, the maximum index you can get is the middle, middle dimension.
If you have such an angle decomposition, you prove that these like chords, like these Lagrangian chords.
Yeah, exactly. You get the Lagrangian chords, yeah,
No,
skeleton, yeah.
Is the statement that they generate the category? Or no?
Oh, exactly. I'll say that later, but it's like the co-core generate the pattern. You have the core is like you see.
You have a critical hints.
So you have, yeah, so the critical maybe co-core. So for example, my handle attachment is this, and this is what you say the core of this thing. Then the phi category is generated by the co-core of, so like the non-compact Lagrange. Yeah, because usually this is not a Lagrange submanifold, it's usually singular. Only in special cases.
So it's like the cone of the Legendre. Okay, sorry.
Yeah, here it's it's like a cone. Here is like the cone of the Lagrange. Yeah, but I would state the statement. Okay, so so then now a Liouville sector, so a Liouville vector, Liouville Weinstein sectors. So I will not say very precise what this is. So, but the rough picture is that. So this is a generalization of Liouville manifold, but you might have some real boundary of it. Okay. And then so for here, this dashed part, this is called maybe infinity boundary. This is called like maybe finite boundary of X. So this part is still contact as before. So the Liouville vector field is going outward everywhere. But for this part, the Liouville vector field is like maybe tangent to it. So then it's no longer a contact type boundary. And here this boundary should be like the product of a Liouville hypersurface. Maybe say a Liouville manifold times R. So it's like this structure. That's the rough idea. And indeed, one can always construct such a sector from starting with a Liouville manifold and then delete a neighborhood of a Liouville hypersurface. Choose a Liouville hypersurface. So that means a hypersurface where alpha restrict to give you a Liouville manifold, and then delete a small neighborhood of it, and this will be a Liouville sector. And then Weinstein is similar, so except every other place is replaced by Weinstein hypersurface. Okay. Great. So this is sector. The sector. Okay. Great. And the example, basic example that is relevant to our classes. For example, this T star T. This is a Liouville sector, or maybe generalized Weinstein sector. So yeah, because so this T is you decompose as the compact part times maybe the real part, which is like r plus the n, something like this, and then this. Then bundle is just the product within this bundle, and then this. So for this part, I have a non-compact manifold, right? Then the natural thing to do is that for its potential bundle, what I do is I just add a boundary, the finite boundary on the boundary of this thing. So here, what I do is I compactify this let me say cube, open ball or open cube. Then that to be a closed ball, and then take it cotangent bundle with boundary the cotangent fibers over the boundary of the ball. Yeah, so this works for any manifold with boundary. For any manifold with boundary, you can just do this. Its cotangent bundle will be a dual sector. GPRT, and then you can, and then any product of dual manifold or dual sector will be a dual sector. So then let me just before everyone gets too tired, let me just jump to the geometry, dual sector, or whatever geometry for this universal centralizer. Okay. Then, so maybe just specialize for SL2, which explains the general picture. Okay. So recall that we have this integral system picture that we have generic fiber torus, metal torus, and then central fiber 2 copy of A1. And then there's one little thing to do, because since this JG is from like some Hamiltonian reduction by cross n, right? So then this naturally mapped to maybe the coset n mod G mod n mod n. Pick any you could see, and then map to R in it. Then this gives a Burhat decomposition for JG, and then a general, and then a result is that this this image actually only covers W of the form W, the longest element times the longest element for a standard length. So simple. So each one is indexed by subset S. And then now let me just say what is this in this picture. So but here the situation is easy because we only have two elements, the identity and then the other generator. And then the identity one will correspond to this two constant section. Okay. So these are the identity one, and the complement will be the other element, the longest element. Okay. And the nice thing is that one has a explicit description for this Broad decomposition, and let me just say what is this in this case. So if we do W0 here, then it corresponds to the complement of these two constant sections, and then the claim is that this naturally identified with the cotangent bundle of the maximal torus. So then, yeah, so here I can represent. So if I do the standard coordinate, B is C star and X and C, and then here what I assign this here is this element. Assignment, which in this one is actually not a centralizing pair. If you want to centralize it, you replace this by 2xb. So what I present here is using the Hamiltonian reduction description.
If this isomorphism is symplectic.
Yes, symplectic.
I
Yes.
see.
Yeah. Great. Yeah. So then this and then one can say what is the C star action here. So C star and then it's true to here. So it's slightly different from the usual C star action that dilate the fibers. But here the C star action is actually correctly. So then it's like both dilate this fiber and also shift this maybe negative. That's like something like this is the base, so it's like dilating, but also shift on. Okay. So so then here, yeah, maybe and then I just quickly summarize. So from here, what I want to say is that from here, actually, you can already see some kind of what we should do to make it Liouville sector. So in this picture, the C star action is doing this. Right? So the upshot is that the first, this is not a Liouville manifold because you see that C star action is like expanding on horizontally, but like shrinking on vertically. Then the complexification that we do is exactly like adding some real boundary here. And then the nice feature about this picture is that here you actually see an index 2 handle here. So if I actually I can define some smooth contact hypersurface, which is exactly like homotopy, I mean, diffeomorphic to the removing of these two. So I remove these two constant sections. So then the boundary, maybe the real boundary will be like this hypersurface, okay. And then the JG is from like attaching two handles here, and then this is the handles, and then the other place is just by completion by the. So here is where the handle come from, and And for this, for the part away from these two sections, what we get is exactly can be understood from this picture. So T star T. Okay. And here, unlike the previous situation, the thing that we get is that using some coordinate is that is a T star S1 times something like such a manifold. And for this one, maybe you can identify with T star positive R, so the positive cotangent bundle of R. That's good. And then we just do a we just do a classification to be here to be the real part less than 0. So rectify this T star this part by half disk or half plate. That's the okay. And then we can understand this Weinstein sector completely, because then it's like this product, and then lastly we attach two handles to it. Then that's the picture. And in general, you can do similar things. So you delete the constant section for general G, and then what you get is a Liouville manifold times similar as this thing, and then you just do the same complexification for the second factor, and then you get the product, and lastly you attach attach a bunch of critical handles. That's the handle attachment description for this universal section. And then
I mean, maybe another couple of minutes.
Okay, great. So maybe let me just comment on previous questions. Then using this description, one can show that these constant sections, which are co-cores for these critical handles, generate the Fukaya table. And then maybe last word. So then for this adjoint group, so you only have one constant section. Then center is trivial. So then it's generated by one Lagrangian. Then it's just the equivalent calculates the endomorphism of this Lagrangian. And this involves some wrapping that I don't have time to discuss, but I'm happy to answer any questions. Yeah, and then yeah, maybe I will stop here and then see which question people. Thank you very much.
All right, let's thank the speaker for a great talk. All right, are there any questions?
Oh yes, Valoria, please.
No, I was just clapping for now.
Oh, okay, sorry.
Thank you for the talk.
Okay, thank you.
Yeah, I have a question.
Uh-huh.
So these Lagrangians, they don't intersect, but they intersect like at infinity. Is that?
Oh, because for this wrapped, you need